Did you know that the Andromeda galaxy is moving toward us so fast that every second it gets about 110 kilometers closer? Yet you'd need to wait over 4 billion years to actually notice the difference? The Andromeda galaxy is our cosmic next-door neighbor. If you've ever stood under a truly dark sky, far from city lights, you might have spotted it, just a faint, misty smudge hanging quietly in the darkness. Easy to miss. But here's the wild part. That subtle blur is a colossal spiral galaxy, wrapped in smaller companions, packed with globular clusters, and filled with more stars than we can realistically comprehend. And behind that calm, hazy glow, there's movement. Andromeda is drifting toward us. Slowly, yes, but in cosmic terms, the approach has already begun. The Milky Way and Andromeda are on a long, inevitable path toward each other. Now, sure, there are dozens of dwarf galaxies closer to us, but when it comes to massive spiral galaxies, Andromeda is the closest heavyweight in town. Aside from the large and small Magellanic Clouds, mostly visible from the southern hemisphere, no other external galaxy shines as brightly in our sky. Between October and December, from a properly dark location, you can see it with your naked eye. Just a small, glowing blur. Add a simple pair of binoculars, though, and suddenly that blur stretches out. It becomes structured, defined, real. And here's what makes that even more astonishing. It's about 2.5 million light-years away. Its apparent magnitude is around 3.4, and the human eye can detect objects down to magnitude 6 under ideal conditions. That makes Andromeda the most distant object you can see without a telescope. Even more surprising? Its apparent size in the sky is actually larger than the full moon. Most of its light is just too faint for our eyes to fully register unless the viewing conditions are perfect. Andromeda and the Milky Way are the two giants of what astronomers call the local group, a family of galaxies bound together by gravity. But between the two, Andromeda wins in sheer scale. The Milky Way contains a little over 100 billion stars across a disk roughly 120,000 light-years wide. Andromeda? It may host close to 1 trillion stars and stretches about 220,000 light-years across. That's not a small difference. That's enormous. To put that in perspective, imagine trying to travel there. A spacecraft moving at 17 kilometers per second, about the speed of Voyager 1, would take roughly 40 billion years to arrive. That's longer than the universe has existed. Even traveling at the speed of light, the journey would still take 2.5 million years from our perspective. Relativity would make the experience different for whoever was on board, but from here, that's the timescale we're dealing with. Like our galaxy, Andromeda has its own collection of satellite galaxies, more than 20 confirmed so far. Two of the most famous are Messier 32 and Messier 110. Messier 32 may not always have been as small as it appears today. Evidence suggests it was once much larger, but gravitational interactions with Andromeda stripped away much of its outer structure. That interaction likely sparked intense star formation in its core. Messier 110 also shows signs of being shaped by these gravitational encounters. In fact, astronomers have detected streams of metal-rich stars in Andromeda's halo, likely remnants of smaller galaxies that were torn apart and absorbed over time. Dust observed in Messier 110 hints at relatively recent stellar activity, reinforcing the idea that these galaxies continue influencing one another even now. When we compare Andromeda to the Milky Way, another interesting contrast appears. Andromeda seems dominated by older stars, many over 7 billion years old. Its total luminosity is about 25% higher than ours. Yet the Milky Way is currently forming stars at a faster pace. Our galaxy creates somewhere between 3 and 5 solar masses worth of new stars every year. Andromeda produces closer to 1 solar mass annually. That suggests Andromeda had a more active, energetic past, while today it's in a calmer phase. Meanwhile, the Milky Way is still buzzing with relatively stronger star formation. Then there are Andromeda's globular clusters, about 460 confirmed so far. One in particular stands out, Mayall 2, also known as G1. It's extraordinarily massive and luminous, brighter than any other globular cluster in the local group. G1 contains millions of stars and shines roughly twice as brightly as Omega Centauri, the largest globular cluster in the Milky Way. Its complex structure and multiple generations of stars raise an intriguing possibility. It might actually be the stripped-down core of a dwarf galaxy that Andromeda swallowed billions of years ago. Studying Andromeda's spiral structure isn't easy because we see it tilted at an angle. But processed images reveal two main spiral arms stretching about 13,000 light-years, traceable to roughly 1,600 light-years from the core. Infrared observations from the Spitzer Space Telescope show these arms emerging from a central bar and crossing a vast ring of material. They aren't perfectly smooth. Instead, they appear segmented, with irregular patterns along their length. And at the heart of Andromeda lies one of its most intriguing mysteries. In 1991, the Hubble Space Telescope captured detailed images of its nucleus. What astronomers found was unexpected. Two bright concentrations of stars separated by just 4.9 light-years. The brighter region, called P1, is slightly offset from the galaxy's true center. The dimmer region, P2, lines up with the central supermassive black hole. One leading explanation suggests there's a disk of stars orbiting that black hole on highly elongated eccentric paths. Because stars in such orbits spend more time at the farthest point of their trajectory, they appear to cluster there, creating the illusion of a second bright core. So that faint smudge in the night sky? It isn't just a distant galaxy, it's a colossal system larger than our own, a galaxy that has devoured others, a galaxy still evolving, and one that, slowly but inevitably, is on its way to meet us. There's also another fascinating idea about Andromeda's strange double core. Some astronomers suggest it could be the aftermath of a past merger between two supermassive black holes. When black holes collide, they release enormous amounts of energy in the form of gravitational waves, ripples in space-time itself. That kind of event could have dramatically reshaped the distribution of stars in the galaxy's nucleus, leaving behind the unusual structure we observe today. And then we arrive at the part that really captures the imagination, the future collision between Andromeda and the Milky Way. By carefully comparing stellar positions over many years, the Hubble Space Telescope has confirmed that Andromeda is moving toward us at about 110 kilometers per second. Its light is slightly blue-shifted, a subtle but unmistakable sign that the distance between us is shrinking. Current estimates suggest the first close encounter will happen in roughly 4.5 to 5 billion years. So, what happens to us? Simulations paint a dramatic picture. There's about a 50% chance that our solar system would be flung much farther from the galactic center, possibly 3 times farther than its current position. There's also roughly a 12% probability that we could be completely ejected from the newly formed galaxy altogether, sent drifting into intergalactic space. That sounds catastrophic, but here's something surprising. Direct collisions between stars are extremely unlikely. Even during a galactic merger, the distances between individual stars are so enormous that most stellar systems would pass by each other without ever touching. Ironically, Earth's fate probably won't depend on that collision at all. Within the next 0.5 to 1.5 billion years, the Sun's gradual increase in brightness is expected to evaporate Earth's oceans and trigger a runaway greenhouse effect. By the time Andromeda finally merges with the Milky Way, the Sun could be up to 40% brighter than it is today. Long before the galaxies collide, Earth's surface will likely be inhospitable to liquid water. The cosmic drama will unfold, but we won't be here to see it. As for the final result of this grand merger, simulations suggest the combined galaxy may become a giant elliptical system, possibly less densely packed at its core than many ellipticals we see today. If enough gas remains, it could instead form a lenticular galaxy, or even, over about 150 billion years, evolve into something resembling a massive superspiral. Eventually, the other galaxies in the local group are expected to merge into this structure as well, completing a long chapter of galactic evolution. So when we look at Andromeda, we're doing something extraordinary. We're looking at both the past and the future at once. The light reaching our eyes left that galaxy 2.5 million years ago, before modern humans even existed. And yet, in that same faint glow, we're seeing a preview of our galaxy's destiny. On a human timescale, it all feels impossibly distant, almost irrelevant. But on a cosmic scale, the story is already in motion. The universe is not frozen. It is dynamic, restless, constantly reshaping itself. Galaxies collide, stars are born and die. Entire structures transform over billions of years. Earth is just a tiny grain of dust orbiting an ordinary star, located in the outskirts of a galaxy that itself is overshadowed by a larger neighbor. And yet, recognizing that smallness is one of our greatest achievements. We are the part of the universe that became aware of itself. The part that can measure 2.5 million light years, calculate the mass of distant galaxies, and decode the structure of a nucleus we will never physically reach. The human mind, fragile as it is, stretches far beyond our physical limits. And when we begin thinking about life beyond Earth, Andromeda changes the equation entirely. With roughly 1 trillion stars, about 10 times more than the Milky Way, the scale becomes staggering. Even if life is extraordinarily rare, 1 trillion stellar systems make the complete absence of life statistically difficult to imagine. The numbers alone shift the probabilities into breathtaking territory. Life on Earth took billions of years to evolve from single cells to complex organisms. Andromeda's long-term stability provides immense spans of time for similar processes to unfold. It's entirely plausible that civilizations could have emerged there, looked up at their own night sky, seen the Milky Way as a distant smudge, and vanished back into cosmic dust before Earth had even formed. When you look at Andromeda, that faint, diffuse patch of light, you're staring into the abyss of time. You're seeing ancient light that carries the outline of our distant future. Our existence is brief, almost immeasurably small in comparison. But the fact that we can understand galaxies that will collide billions of years after we are gone, that gives profound meaning to the short moment when the stage belongs to us. If you enjoyed this journey through space and time, don't forget to subscribe, leave a like, and share the video. Thank you for watching, and I'll see you in the next one.